Okay, hi. I want to talk to you about Helene, and she's quite an eyeful, so I'm going to spend some time today talking to you about some of the work that we are doing to uncover some of the mysteries of this object. I'll tell you right off the bat, we still do not know what's going on, but we're making quite headway in terms of coming up with scenarios and constructions to make sense of this object. So let me give you a couple of things. As you can see, it's the scale of Helene is on the order of 40 kilometers. It's oblong, and it's the leading Trojan moon of Dionne. It sits in the outer part of the E-ring, which is also a clue which I don't think we're going to make use of in our current modeling efforts, but if there's time afterwards, I'll tell you a little bit of some of my ideas about how that might play a role in what's going on in a more subtle sort of fashion. You see approximately the surface gravity is on the order of 5 millimeters per second squared. It's an interesting point to notice that actually the surface gravity here is the geometric mean of like typical planetary gravities and microgravity environments. So I don't know if that's really means a lot necessarily, but to me it's suggestive that we may be in an interesting transition zone as far as geomorphological processes are concerned, which is some of the things I'm going to address. Other points are that the images that we have are from Cassini, 42 meters per pixel, and it's tidally locked. Okay, so let's talk a little about the surface morphology. First of all, there are, as you can see, several broad depressions throughout the surface. And it's quite indicative that there is has been or are ongoing processes involving mass wasting and erosion. Especially if you look between the crater walls, you see the appearance of what looks like slumping. It's suggested that the crater walls are in fact retreating. But of course, the highlighted features are the things that are of interest to us, and it would be to interest to anybody who notices that it looks like there is appearance of flow-like patterns on the surface. In addition to that first of all, the kilometer and these grooves that you see, which I'll talk about in a moment, I'll show you an image in the next slide. These extend for about a kilometer, several kilometers, and they have a relief of about 50 meters. So this is also quite fascinating. Like under these conditions, this is not something you would expect to see. The appearance of flow, essentially. A couple other points. There is also evidence, or at least the appearance of mantling of recent small, teeny tiny craters over the surface. That's the one that kind of sticks out, suggestive of that this body is actually also receiving material from outside as well. And then lastly, the high reflectance of the materials involved gives us some upper limits as to the size of the grains, perchance, that are covering the surface, from 1 to about 100 microns. But of course, these are just loose constraints that we're essentially working with. Paul Schenk took many of the images we have and of the stereo images and constructed some DEMs of them. And I have some transects of the surface here. Let me just point out to you, that's a blow-up of this region. And so I have a number of transects of that image. Here, the ground tracks are shown here, and the actual transects are shown here. And so a couple of points I want to point out. Number one, this relief scale of about 50 meters is a number that I'm going to make use of when I start going into the plastic model that I'm going to apply. This relief scale here, so this is for transect F, and it starts over there, so the beginning there, 0, is corresponding where the F is located on the image, and it cuts across there. And so essentially you see that this major bump here is this associated actually with that guy, not with the K bit. It's actually this section over here and cuts across there. So the 50 meter, that's the only constraint that I'm going to have in any of the subsequent modeling that I'm going to be doing. The other point to keep in mind is that the broad depressions have a grade of about 4 to 6 degrees. So it's not much larger than that. Of course, there are steep sections that can exceed 10 to 12 degrees, up to even 20 degrees. But I should note that in processes that we're familiar with from planetary scale geology, you would expect if there was, for instance, an angle of repose, lots of these structures here are well below the angles of repose, which would be about 25 to 30 degrees, depending on what you're talking about. So it kind of adds to the mystery, which kind of got me very interested. So about a year ago, I had a meeting with Danielle Weyrich, and she is working on studies of lunar regolith materials under loose packing conditions. And she is starting to see that, in fact, these materials are starting, they appear to behave like a Bingham, have Bingham-like properties, meaning to say it has plastic features. And in the sense of what we're going to be talking about, that means to say is that you need a minimum stress downslope before you get any motion to take place. And when we were thinking, and when one thinks from henceforth, when we speak of non-Newtonian materials and so on, in my thinking, the physical process that's of most importance in my thinking is that for a given sloping angle, there is a minimum required depth of the material that's moving in order for flow to begin. If the depth is too shallow, then nothing will happen. It basically sticks and stands up and can actually maintain relatively high angles of repose. So our working hypothesis is the following. The mysterious, loose, smooth, icy dust on Helene behaves as a non-Newtonian creeping flow, creating the visible flow patterns that we see. So what have we done? We've taken MARSSIM, which is a community-wide, as far in the geomorphology community, used code, which is a landform evolution model. And Alan and I have implemented a routine that actually mimics, represents, models plastic flows. So essentially, there will be a quantity which we call regolith, and this regolith flows according to mass wastes, according to this plastic prescription of either a Bingham flow or a Bingham law or a Glen law. Another analogy I forgot to mention is you could basically think of candle wax or glaciers. I'm not saying that there's glaciers on Helene, but we're just simply saying that the processes are very akin to such things. The other thing is we took, so essentially these are vertically integrated so that we get essential mass fluxes from that. And essentially this nonlinear shear thinning flow is now ready to go. And so what we are now at the stage of doing is exploring a whole sequence of scenarios, because we're still basically in the dark. Now, the one constraint I'm going to be using in any of my modeling in this respect is to assign that you saw the 50-meter relief scale that we were talking, that I showed you, representing the height of those grooves. That can be translated to the minimum depth I need for motion to occur, given a blah-de-blah slope. So I've done that, and I've scaled it up accordingly because it's a general feature. And so it's basically the minimum, it translates to a minimum stress. So I can extract such a thing from that relief feature. And then that's what goes into the models. So now, here are some of the things that we've done. I'm almost done. I'm going to whip through our results. I'm considering a couple of scenarios. I'm considering what I call bedrock icy surface, as you see there on the left. And I suppose that through some means, the surface materials become liberated through some weathering process. And that surface material, which I now call regolith, can actually then move according to the nonlinear mass wasting algorithm procedure that we've implemented, representing Bingham flow or plastic flow. Now, in addition, I'm also looking at a parallel scenario where you have ongoing weathering. Oh, and one might ask, what is the source of that weathering? Well, it could be micrometeorites, if there's a steady source of weathering, or it could be maybe some catastrophic event, like a big meteor strike, which then, in an instant, liberates a certain amount of material uniformly over the surface, and so that's ready to move around. So we are going to be exploring many branches of scenarios here, but right now I'm going to show you just some of the very basic ones that we're looking at. In addition, we say that this material this body can also receive material kind of raining snow like dynamic, if you will, and that's going to be treated as well as a regolith property behaving as this Bingham fluid. Let me show you first the regolith production and transport. Here on the left, I show a case for all other parameters being equal. I show weathering only at 95 million year and 130 million year phase. And then on the right parallel here, I show where you have accretion and weathering going on. Never mind the numbers for now, because that requires a longer talk. One of the conclusions that we're coming away with at this stage is that whatever we see here is probably, if we're to accept this as a plausible setting, that means we need both accretion and weathering to take place. This is the large crater basin there in that original image here, this bit here. And if you look closely, you're starting to see the emergence of flow down slope. So essentially it's creeping flow down slope like that of candle wax. And so I think that's kind of cool. It's very encouraging. Here, let me show you an evolution of the elevation morphology over time. So that's that crater basin here to the left again. And these are a sequence, 50 million, 90 million, 120 million year. And if you look closely, you can see essentially what's happening is that the weathering liberates material from large slopes and they move down, but their movement downslope is enhanced by the additional rain of material coming down because it causes the thickness of the regolith to exceed what's necessary for flow to take place. And if you look, you can see in the basin, you see the beginnings of the early stage and slowly filling it up. And similarly over there, you see the generation of this regolith material, and it's creeping down slope and slowly filling out the basin until the point where you see very strong divides and clearly lines along the topography, which would say, if you were to throw other things down on it, would follow those paths. And material henceforth would follow such paths. So, yeah, and here's my last point. And then this was interesting. I made a measure of the traffic flow, the amount of material crossing grid points at every time step. So basically like traffic. And it's kind of nice what you see here. Here's a case for just weathering, and here's the case for weathering and accretion. And you see that there's actually bursts of activity. So it's both steady and unsteady in a sense. And these bursts that we see are associated with slips in the material. What will happen is the material will grow because of rain or because of weathering, and eventually it will cross the threshold, and then it'll be a jolt, and then it'll slow down and stop even, and then it'll happen again. And these will happen in localized spots, kind of seismic-like activity. There's also crater retreat, but I'll just jump to the conclusions. So we are still considering, we've adapted a non-Newtonian creeping flow model into MARSSIM, and we're applying it to Helene. We are exploring a whole bunch of scenarios. We're still at the early stages, but we're getting close to getting initial set of stories out. Current indications show that accretion is necessary and that the flow regime is non-steady. And please contact me if you would like to know more about this. Thank you.
Do we have a quick question for the speaker?
Has Helene been in the same location all his life, or has it moved around? Could that make some changes?
I don't know if it's moved around. I think there are people in the audience who might be able to say something about that. But if it is moving around, it could be a source of sweeping up of material, because its orbit is stable, but it could have large amplitude oscillations, and it could be sweeping up material, and then it could stop, go again, stop. Yeah.
Interesting. One more question.
Yeah.
How big was the flat surfaces bounding the flow channel?
I'm sorry, say again?
How were the flat surfaces bounding the flow channel? I see there's lots of flat inclines that were above A.
In this one?
No, I mean, observational, there's lots.
Oh, right. So these bits here. Yeah, exactly. Yeah, no, that we don't know, and it could be because you might be generating, let's say, you hit it really hard with a meteor, and you might liberate a lot of material at the top, and that might also behave in the classic mass wasting sense to form these fans. This could also just be infill over a long time. I've only run these simulations for very short periods of time. It's nonlinear. It's a nonlinear diffusion equation, so you have to take very small time steps.